In this demonstration of Dynamic Designer, we're going to simulate a simple clamp mechanism. There are two main objectives for the simulation. The first is to determine the input to output clamp ratio, and the second is to transfer the loads from a critical component into a solid edge simulation FEA study. To get started, we can simply click on the Tools menu and then click on the motion icon. This launches the Dynamic Designer browser. We can then start a new mechanism. We can choose to automatically add parts to the moving or grounded nodes on the browser. If we say yes, Dynamic Designer automatically determines whether or not a part is free to move in the solid edge assembly. If it is, it's considered a moving part. If it's fully constrained and cannot move, it's considered a grounded part. In that process, Dynamic Designer also converts all the assembly constraints into corresponding Dynamic Designer motion joints. If we look on the Joints node in the browser, we can see all the assembly constraints converted into corresponding mechanical joints. If we return to the solid edge assembly and change any of these constraints, the change will reflect back into Dynamic Designer. The first thing we'll do is we'll go ahead and we'll set some simulation parameters for our upcoming simulations. First, we'll define the direction of gravity relative to the global XYZ position. In this case, we'll choose -y. Next, we'll set the simulation duration to be 2 seconds, which will allow us enough time to cycle our actuator forward and returned. And we'll choose 200 frames as our output. This number will control the resolution of our video files that we might create into AVI files. It also controls the resolution of our plots and the quality of our animation playback. Last, we'll make a couple simple changes to our solver accuracy settings to prepare for this particular example. The first thing we'll do is we'll go ahead and we'll simulate the mechanism just using gravity. We'll stop the simulation immediately by clicking on the icon again that we started the simulation with. Click, hold, and drag the slider button back and forth to replay the animation. You can also click on the slider button once and then roll the scroll button on the mouse. We can see in this case there are a few components that are not constrained properly. We can either go back to the solid edge assembly and add the appropriate constraints. We can add the constraints here in Dynamic Designer by right-clicking on Joints and adding the appropriate joint, or we can attach the parts rigidly to other parts in the model and treat them as subassemblies. For this example, we'll do the very latter case. We'll attach the two red wear blocks to this piston subassembly. We can click on the two wear blocks holding down the control key, click, hold, and drag with the mouse onto the piston assembly, and then release the mouse button. These parts are now rigidly attached to that subassembly. We can do the same for the two blue links. We'll treat the blue links as one unit. We can click, hold, and drag the one link onto the other link. The last change we'll do is we'll attach this blue arm to this gray clamp shaft. We can click on the arm, drag and drop onto the clamp shaft, or an alternative way is to simply right-click on the arm, choose Attach To, and choose Clamp Shaft. If we go ahead and simulate again by clicking the Simulate button, we can see that we've properly constrained our parts. Clicking the button again will allow us to delete the results. Now that our parts are properly constrained, we'll go ahead and we'll apply a motion to our piston. We can apply motions directly through the joints in Dynamic Designer. We can also apply motions on parts directly. In this example, we'll put a motion on this constraint that attaches the piston to the cylinder housing. We can right-click on the constraint, choose Properties, and change the motion type from free to displacement. In this example, we'll use a step function and we'll step at 65 millimeters in 1 second. In this case, we choose a negative 65 so that we oppose the direction of the arrow as indicated here on the graphic. We can apply that motion, and we can also preview it by clicking on the preview icon. To add our return stroke, we can change this step function to an expression. The step function is added into the expression window, and now we can continue to add additional statements onto this expression. For this, we'll simply define a return function to return the actuator. If we go ahead and apply, and then run our simulation, we should see our changes. We can plot characteristics for any part, and we can also plot characteristics for any joint. In this example, we'll plot the translational displacement for the actuator simply to verify our input was what we'd expected it to be. If we click on a plot, it will move the model to that corresponding position. We also have a red tracer on the plot, so if we click, hold, and drag the slider button, the tracer follows the plot. If we hover the mouse over the graph, we'll get a flag of the numerical values. If we'd like to delete a plot, we can simply right-click on it and choose Delete. Or we can also do those sorts of actions down here under the Plots node. Now that we've defined the proper input for the actuator, we'll go ahead and we'll apply a clamp force. To do this, we'll delete the results, and we'll turn on two components that are currently hidden. We've added a clamp post in here simply to represent the actuator clamping on some sort of a fixture. Before we add the contact between this clamp pad and this top post, we'll go ahead and we'll add a spring in between the top post and the bottom post. Simply click on the two components and then click on a circular edge for which to attach the spring ends to. Dynamic Designer will create a simple spring graphic. It is not a solid edge part. The first three parameters in the spring dialog box control the mathematical representation of the spring. We can define a stiffness, the free length, and any preload force in the current condition. The remaining three fields control the graphic only. We can specify the coil diameter, the number of coils, and the wire diameter. Lastly, we'll go ahead and we'll define a collision between the clamp pad and the top post. We can right-click on Contact and choose Add 3D Contact. Click on the two parts we'd like to collide. Define any material characteristics between the two parts using custom values or using values from a library. We can turn friction on or off, and in this particular example we'll turn friction off as it's not important to this particular simulation, and it saves simulation time. We'll go ahead and we'll simulate now with our contact in place. Now that our simulation is running correctly, we'll go ahead and we'll plot the input force. A great feature of Dynamic Designer is to be able to reverse engineer inputs. For example, we can plot the required actuator input force needed to cycle this mechanism. The same is true for motors. To plot the input force required to stroke the mechanism forward and return it, we can simply right-click on the joint which had the motion applied to it, and we can plot the motion generator feature. These values are taken relative to the global coordinate system. We can see the maximum load case condition is when the clamp pad is fully compressing the spring. By default, Dynamic Designer will plot all its values with time on the horizontal axis. To plot the ratio between the two, we wish to replace time with the clamp force for the contact. Before we do that, we'll go ahead and we'll add force graphics or vectors for the contact force. To do that, we can right-click on the clamp shaft or the clamp block, choose Add Result Object, Reaction Forces. Notice the graphical vectors that just appeared pertaining to that part. Vectors also appeared for this arm because the clamp pad is rigidly attached to the arm as well. The vectors will scale in size depending on the force behind them. In this case, the vector will be at maximum length when the contact force is greatest. If we scroll down to the bottom of the browser and look at the reaction force node, we can see it's been populated with a few different forces. The contact force we wish to plot is right here. If we can right-click, choose Plot, Magnitude, and we can see that force. What we ultimately wish to do is plot the input versus the output on the same graph. So let's delete the plot we just created, and let's click the plus sign next to the plot that's currently on the screen so that we see time and axial. We can click on the contact force, hold the mouse button, drag and drop over time, and release the mouse button. You can see here we've replaced the time component with the contact force component. Now we're able to see the ratio between the input and the output. Not only is it nonlinear in nature, but it's also a mechanical disadvantage in this case. In other words, a given amount of output force is going to require almost double the amount of input force. A nice feature of Dynamic Designer being fully embedded with Solid Edge is that a user can return to the Solid Edge assembly now, make changes to any of these links, return to Dynamic Designer and run a new motion analysis, and compare the new against the old results to determine if those changes are affecting the model in a positive or a negative manner. The second objective of this simulation was to apply loads from this clamp shaft component directly into a Solid Edge simulation FEA study. We'll go ahead and we'll delete the simulation results and we'll prepare the part for the load transfer. But the first step in the load transfer is to define the load-bearing faces for all the forces that will occur on that part. Since we'll pin this cylindrical face in our Solid Edge simulation study, we do not need to define load-bearing faces for this large cylindrical face here. On the other hand, we're going to transfer the loads here between the light blue toggle links and the clamp shaft part right at the revolute joint location. We can right-click on that revolute joint, choose Properties, click on the FEA tab, and then define the load-bearing faces on the clamp shaft component. So we selected the inside cylindrical face. We can rerun the simulation and then create a plot for that joint to determine exactly where the force is maximum. We would expect it to be when the spring is compressed in its maximum position. Another feature we can use here is the Animate While Solving. We can turn this feature off and then we can run our simulation. This allows us to run the simulations much faster without playing back the animation while it's solving the mathematics. We still have full access, however, after it's complete, to the animation. If we now right-click on that revolute joint for which we define the load-bearing faces, we can plot the reaction force for that joint. And we can see at what point the load is maximum. Additionally, as we did for the clamp pad, we can also plot the load vectors for the clamp shaft part to visually verify the directions of our loads. Simply right-click on the clamp shaft, add result object, reaction forces. To help get a better visual of those forces, we can do two things. The first is we can change the color of the force graphics. And the second is we can hide all other components except the clamp shaft. We've essentially viewed a free body diagram of this part in its current load position. We've already defined our static study for the solid edge simulation, and now we'll simply go ahead and we'll right-click on the clamp shaft part underneath the static study and choose Add Loads. This automatically adds the loads into the solid edge simulation study. The load directions appear different here because they are taken relative to the original orientation of the part. If we now exit the motion environment and look at our solid edge simulation study, we can see that the loads have been applied automatically to this component. We can simply add our pin constraint to the shaft and mesh and run the part. This concludes this demonstration of Dynamic Designer.